My name's Brian McCord. I'm the lead economist here at Digital Catapult. And I'm very, very pleased to welcome the 5 speakers that we have on our panel. We'll move swiftly on, and I'll introduce our first speaker, which is Professor Alan Kerman. Alan is Chief Economic Advisor at the New Approaches to Economic Challenges at the OECD, and is Professor Emeritus of Economics at the University A Marseille. And I'm going to stop sharing and hand over to Alan now, and I will be running Alan's slides for him. So,
thank you so much for inviting me, Brian, and it was very interesting to hear Andy again, who was a pioneer in this field. So I should just say a couple of words. Could we have a next slide, Brian? About where I'm coming from. The OECD has a thing called NICE, New Approaches to Economic Challenges, for which I am the chief advisor, I'm told. But this NICE program has encountered a lot of opposition at the OECD for all the reasons we've just been discussing about inertia and so forth. But nevertheless, it started to get a lot more traction just recently. And it's called, of course, NICE. And when we coined that name, I suggested that we take as a slogan, just do it. But somebody told me that some other organization has already taken that slogan. Next slide, please. So what is it that we run into difficulties with in standard economic models? And I think that the first problem, I think you jumped a slide there, Brian. Could you go back one? There we go. So what are the things that make us look at ABMs rather than standard models? The first one is what's called non-ergodicity. Our social economic system is not ergodic in the sense that the stochastic framework changes over time. So this is a problem for economists that we've always faced. And Samuelson once said, without ergodicity, we lose econometrics and economics becomes history. But ABM models are a way out of that trap. So we don't just have to think of a model which is sailing forth on an equilibrium path and then occasionally gets knocked off it. We can actually think about one which is evolving over time and adapting over time. Second observation, heterogeneity. One of the difficulties that economists, particularly macroeconomists, have had is dealing with the fact that the people, the components of the system are very heterogeneous. And as a leading medical authority said, as physicians, we're ambivalent about heterogeneity in medicine. We actively suppress it because if you have heterogeneous patients, you can't have a uniform prescription for them. And that's a problem that we run into all the time in economics. And as soon as we drop our interest in heterogeneity, we of course have to put on one side all the problems of inequality and the differences in the people who are faced with different crises. Next thing is computational irreducibility. This suggests that the model has dimensions and characteristics which make it impossible to reduce it and then solve it. And so you simply have to simulate it. And the only way to understand what's going on is to simulate the model many times and understand the patterns. Okay, next slide, please, Brian. And then the last thing is emergence. Aggregate systems, macroeconomic systems, have properties that emerge both over time and as the number of components in the systems increase. And you cannot, by looking at the individual components, deduce what's going to happen when you get to those higher levels. So you have to study the problem as one in which individuals, components interact and new phenomena emerge, which you couldn't have got from looking at the individuals. You cannot understand the structure of an anthill by looking at individual ants. Next slide, please. And so it was Phil Anderson, Nobel Prize winner, who said, you know, the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. And as economists, we have a tendency to do that. He said, in fact, the more the elementary particle physicists tell us about the nature of the fundamental laws, the less relevant they seem to the real problems, particularly those of society. And at each level of complexity, entirely new properties appear. And understanding that requires research, which I think, he said, is as fundamental in its nature as any other. Next slide, please. So what about innovation, which I'm supposed to be talking about today? And it's often been modeled as an evolutionary process. Everybody here remembers Nelson and Winter and Brian Arthur and all those people, Giovanni Dozzi, and that's a long tradition. And now, of course, we've moved way beyond that. But still, there's this idea that what happens is you have sort of existing mechanisms for looking at things, for producing things, and every now and then there are mutations which yield innovations. And then, of course, the question is how to explain where those mutations happen and how fast they happen. Typical example was the introduction of the COVID vaccine, for example. Just think about that. We need to evaluate its protective effectiveness, how it actually protects the people vaccinated, its capacity to inhibit transmission, which is perhaps even more important, the speed with which it can become widely available, and lastly, the proportion of the population that would take it up. And there we see the problems that you have in all these complex systems of feedbacks. Let's suppose something goes wrong with the early versions of the vaccine. That will generate a feedback to the population which says, well, we can't really trust these medical advances, so we don't want to be vaccinated. And there's already a powerful anti-vax population around. So if we add to that nervousness about the taking up of the vaccine, then we may find that it won't be very effective simply because not enough of the population take it up. And the answer seems to lie to these sort of problems in computer simulations. And they're largely used in modern epidemiological work. And in fact, they've been widely used to try and work out the characteristics of what will happen with a vaccine. Next slide, please. And you see you have another problem, which is political pressure. And you see this poor person who's actually suffering currently from this is trying to push the scientists into introducing a coronavirus by November the 3rd, okay, the election date. And of course, doing that has the great problem that not only do you try and push this thing forward fast, but you diminish public confidence in it. And a group of researchers working on the problem were asked, would you take the vaccine if it's introduced too rapidly? And they all said no. So that you understand the problem that all these dimensions are very difficult to model in a conventional model, but you can easily put those into an overall agent-based model. Next slide, please. And I wanted to give you another example, which I think is very interesting. We talk a lot about how now there's so much information. Everybody's familiar with everything that's going on. But I took part last year in a conference in Beijing on innovation. And there was a discussion about infrastructure and its role in the growth and transformation process. And in particular, the subject of high-speed trains was raised. And there were a lot of people in the room who were experts in that field. And I asked naively why the maglev technology had sort of seemed to have dropped out of the process. And you know, this is levitating trains by magnetism, and then they go at high speed with no friction. And there were plans to introduce them widely, but those plans seem to have been dropped. Next slide, please. So there were very convincing arguments about why that couldn't happen. They said the technology was too sophisticated and expensive, and you have to build new beds to run the trains on. Running trains at 600 kilometers an hour, and when you have to brake the train, is not a trivial matter, they said. And they also said the gain in time is not worth the expenditure. So the technology had been abandoned, and the ambitious plan to build a track from Hamburg to Berlin had been dropped. Next slide, please. So I went back to the hotel, reflected on that, and decided these experts obviously had found the answer to my question. But what did I see when I turned the television on? Next slide, please. Surprise, surprise. CNN. The Chinese are just about to introduce a maglev train, and they're going to build a line from Beijing to Shanghai, and that'll get the time down to 3.5 hours. And almost immediately, the Japanese pointed out that they were doing the same thing. So even in a milieu which is well informed with all the information we have, it seems that somehow innovations can get by under the rug, and people don't or aren't all perfectly informed about them. And I find that another fascinating example in a world where we think that we have everything in sight. Next slide, please. So what I would say is that in a rapidly changing world, we need to have recourse to different approaches. And Frank Hahn, the famous mathematical economist, who really spent his whole life in economic theory and doing mathematical models, said in 1991, when he was asked to predict the evolution of economics in the 21st century, he said, "While there will be work for the computer scientist, I very much doubt that economists will be able to establish general propositions in any but very special examples. Again, I do not judge. Simulation, especially when based on good data, is a perfectly respectable and probably fruitful activity." And everybody was very shocked by that, because we'd been brought up in a world where economists build simple models and solve them and give you the solution. So next slide, please. That should be the end, except to say that people say, well, this is all very interesting, all very exotic, but nobody is really taking this seriously. Here's a list of academic institutions which are taking it seriously. And you can see from various places, from the UK to US, to Japan, to France, to Germany, all working hard on these problems. And then next slide, please. Should be one more, there we go. And these are places with Andy Howley, of course, at the top there at the Bank of England, but these are places that have actually built ABM models and used them. And to some people's surprise, you notice that the Fed and the US Treasury have built these models. Even the Bundesbank has built these agent-based models. And the point is, it gives you a lot more flexibility, and they are not less rigorous than the sort of models that we used to build. And they're different in the sense that if you don't specify everything carefully, they don't run. So in some sense, they're more constraining and more rigorous than our simple models in which we made some assumptions and then simply imposed them and solved the models. So I think that ABM models, particularly for complex systems, are in fact the future. Next, and probably that was the last one. Yes, so if you want to know a little bit more about that, you might look at a book with David Sloan Wilson, an evolutionary biologist, and myself edited, called Complexity and Evolution Towards a New Synthesis for Economics. And we discuss many of the problems that will be brought up today in that book. Thanks very much for your attention.
Alan, thank you very, very much for that. And I'd now like to hand over to Nigel Gilbert, who is a professor at University of Surrey. And Nigel, we'll pass over to you.
Thank you very much. And thank you, Alan, also for introducing this session like that, because what I'm going to do is to take forward what he's been saying and show you how one way in which one can actually model innovation. I'm going to be talking about the modeling of innovation, because innovation isn't just a matter of thinking of bright ideas, as we all know. What is really important in innovation is everybody else, the context in which innovation works. And so I'm going to talk today about what we call innovation networks. In practice, innovation always happens in collaboration in some way or other, through collaboration agreements or just knowledge sharing, people chatting in the pub when we could go to a pub, licensing agreements, venture capitalists and angels, and of course supplier-customer relationships, because if you're going to innovate, you need to be able to sell your innovation. I'll just show you an example of one such thing, the Diagnostics and Research Tools Conference, that's an example of the importance of this kind of networking to innovation. So if we're going to be modeling innovation networks, what do we have to do? Well, the important thing about this is that we can't just model the relationships. It's not just a matter of modeling a social network. We need to, in fact, model things on two levels. First of all, we need to model the market, the producers, the customers. And secondly, we need to model the knowledge. If we're talking about innovation, it is crucially a matter of the development of knowledge. And these two interact. The knowledge that is in innovation leads to better products, different products. The market may or may not take on these products, and so we proceed. And also, we're talking about something dynamic. We can't just model an innovation network usefully at one moment in time. We have to think about it as it proceeds through time. So, in order to do this, what I wanted to talk about was a particular framework for modeling innovation networks. It's called SKIN. It stands for Simulating Knowledge Dynamics in Innovation Networks. And it's an agent-based model, just as Andy was talking about. It's got agents, and the agents are the innovators, the firms, the universities, the research organizations. These are heterogeneous and they have agency. They can perceive their environment. They can see what's going on in their market. They can act by perform by introducing innovative products. They have strategies for creating profits, and they're not stupid. They remember what they know and what they have done. And all of this is done within an environment. So our agents operate within a virtual environment, we might call the corporate world, from which in their interactions within this environment emerges an innovation network. So just as Alan said, the important thing here is emergence, modeling emergence. Well, as I said at the beginning, the important thing about innovation networks is the notion of knowledge. And that means that we have to model knowledge as well as agents. And in the particular way in which that is done in the SKIN model is in terms of something that's called a keen. It's intentionally makes you think perhaps of a gene. The keen is the representation of a firm's knowledge. It consists of a row of triples which specify the elements of knowledge, which we think of in terms of a capability in a particular area, a particular domain, an ability within that capability to perform certain sorts of activities, and a level of expertise in that ability. And so a keen is just a collection of these triples. And every firm will have a different key, or every agent will have a different key, just like every person has a different gene. So how do we model the construction of innovation? Well, we say that each agent has a key. It generates from that key, from the knowledge that it possesses, a hypothesis about an innovative product. We call it an innovation hypothesis because at this stage, the firm doesn't know that its innovation is going to be successful. It thinks it might be, and it tries it out. It manufactures or produces a product and puts that on the market. In more detail, what it does is it finds the appropriate raw materials or whatever it is that is needed to produce this innovation. It estimates a price for that product. It buys the requested inputs from suppliers using its capital. It produces the output, puts it on the market, finds a customer, sells the product, and then if the sales is successful, it may adjust its prices. So a very straightforward kind of model of production. I'm talking about goods here, but this applies equally to services. But I do want to emphasize what is going on here is actually a very complex process. Complex in the sense that there was a lot of feedback going on here. First of all, if the innovation uses or tries to use inputs that are not available on the market, we're going to fail. If the production process is so expensive that nobody wants to buy the product when it's produced, then again, it's going to fail. So there's a lot going on, as it were, behind the scenes here. And also what's going on is a lot of learning. This is a complex system that is changing dynamically and the agents are learning. I've already mentioned that firms learn to adjust by adjusting their prices from their experience, but they're also capable of doing research and development. Their keen doesn't remain constant. They can make changes or incremental learning to their keen to see whether they can produce a better product. They can also say, well, this really isn't getting anywhere. Let's try something completely different. And importantly, they can learn from others, other firms through partnerships. This is where the innovation network comes in. So we have a system where individual firms are constantly changing in a complex environment consisting of all the other firms in our model. And that means that we're also involved in population learning, because some agents will be successful and grow, other agents will be unsuccessful in their efforts, will go bankrupt and effectively remove themselves from the population, remove their keens from the population. And here's a quick, I'm not going to explain all of this in detail, just to show you that this is the model in action, a particular run of a model. You can see the products being produced, various sliders showing with parameters for this model, and the way in which, if you look at the bottom left, you can see the network and a power law arrangement of the emerging network as it develops. Okay, well, this all sounds perhaps a rather abstract, almost academic, you might say. Is this of any practical use? Well, yes. What I've listed here are the titles of papers that a whole variety of people have used the skin model all over the world. Some of these in Europe, some in China, some in South America, some in the US. And what I've emphasized here in this list of titles of articles reporting on the use of skin are the areas, the domains where this model has been applied. And as you can see, it has been applied very widely on all sorts of things, ranging from the life sciences to the development of the internet, defense industry, and even work that we've done on the way in which the policies for developing the Horizon, the European Union Horizon funding program. You can find out more about this model on the web. That's the URL you can use. That the code for the model is open source, freely available, and there is also a bibliography of all the articles that reports that have used the skin model. So to summarize, innovation is embedded in a complex adaptive system and network. Innovation networks can be and have been studied using an agent-based model. And those agent-based models can be used to test policies in advance in what you might call a computational laboratory. But a word of caution, I don't want to say that all of this is dead easy. It isn't dead easy. Building and calibrating and validating these models does take time, however much somebody might be breathing down your neck. You can find out more about using agent-based models for understanding innovation in this book, which was written with Christopher Watts, and that will be me. I hope that's been inspiring. So thank you very much. I will now stop sharing these slides if I can.
Thank you, Nigel.
I'm struggling to stop sharing, so if, my mouse seems to have disappeared. So if
well, that, I mean, that, again, as always, that was really fascinating and a great sort of insight into the work that is being done around agent-based modeling, and particularly within your own research department. And we look forward to being able to discuss this at the sort of panel conversation. I'm going to hand over now to Dr. Lise Boland and Dr. Nigel Shardlow from Sandtable. I'm very pleased to introduce Nigel and Lise because they've been working with Digital Catapult for a number of months now, developing our model for exploring the impacts of the diffusions of advanced digital technologies. So I'm going to hand over to Nigel and Lise, and looking forward to hearing all about our project.
Thanks very much. Thanks very much, Brian. I'm going to share our screen. So, and thanks everybody for coming today. So I'm here with Lise. We're socially distanced in the same room, and we're going to talk you through a project that we've been working on with the Digital Catapult for about 6 months now, and we worked out we've probably got enough material coming out of the work for a 2-day seminar, but we're going to try and get through it in 15 minutes today. It's a model of innovation diffusion. It's similar to the one that we've just seen from the other Nigel. But it takes a different, or it's attacking a similar problem, but from a different perspective. Our focus has been on technology, but we'll get into that as we go through. How do I change that? There we go. Sorry. So quickly, yes, the agenda. I'm going to talk you through the rationale for the project. I'll do this, some of the ideas behind it. Then I'm going to hand over to Lise, who's the data scientist, senior data scientist at Sandtable, who actually built the model. Who'll talk you through its design, implementation, behavior, and how we've used it to answer some of the questions that we addressed for the Digital Catapult. So the goal of the project was to develop an agent-based model of innovation diffusion. And the end game here, as you see, is to help policymakers and agencies, such as the Digital Catapult, understand the impact of different kinds of intervention on measures of innovation activity. And that's something that Jeremy talked about in his opening remarks. And that's what we're trying to do. That's what we've tried to do with the work here. So a little bit about the conceptual foundations for the model. When we're building models, we try to think about the conceptual foundations first before we plow into development, and that's what we did here. We decided quite early on in the project that in order to capture the features of the innovation process we're interested in, we actually needed not one model, but two. What we're presenting here is two models. There's a model of the technology landscape and how that works, relationship between products, technology, and human needs. And we've also got the agent-based model proper, which is a model of companies' activities in that landscape, how they explore that landscape to discover new products. Oops. So, as I said, only the second of those models is an agent-based model. Model of company behavior. This is the kind of theoretical foundation that we built the work on. It's Brian Arthur's work on the nature of technology. I think Alan mentioned him in his talk. And looking at that work, it was what convinced us that we needed to model the technology landscape independently. So Arthur depicts technology development as an evolutionary process. New technologies emerge from earlier technologies through a process of improvement and combination, and that, as we're thinking about this, makes sense to us and captures many of the features of a kind of everyday understanding of technological development that we thought were important. In particular, the idea that progress in one area depends on progress in others. So this is our technology landscape schematically. These will cover it in more detail and how we implemented it later. So you start with the notion of a product, which is kind of one of the key building blocks of the innovation process. We're showing them here as individual disks in a stack. They belong to a specific technology, and you can think of those as the stacks as a whole. And then a product can be thought of as a sort of level of development of that technology within that stack. So bringing it back to reality, within smartphones, products with face unlock, such as, one of the first ones in Apple's range was the iPhone X. They're at a higher level of development than those without face unlock. So each successive or higher product in the stack represents an improvement of the technology. And then products depend for their development on other products. It kind of intuitively makes sense. And those other products may exist within other technologies. So the dependency here we're showing with the blue arrows. So the iPhone X depends on products from many other technologies, and face unlock is only one of those technologies it depends on. And then the other element of this is that technologies and the products within them meet human needs. They fulfill a human purpose. And we're representing the needs here by the kind of pink puddles on which the stacks sit. And as product development advances within technology, the needs are better met. So when we say product, and this is quite important, I think Arthur makes this point as well, we mean type of product. So it's possible that several companies might develop products of that type or at that level of technology. So in our smartphone example, Apple's iPhone X isn't the only smartphone that has face unlock. Other manufacturers have built products with that feature as well, of course, Huawei being one of them. Improving a product, progression up the stack is one form of innovation, but another is to develop a completely new technology or a new stack. And we know that happens. So the red disk is, you can see over there on the right under D, it's a new product in a brand new technology stack. So what might a new technology be? Mobile telephony might be an example of a new technology in Arthur's terms. So for our purposes, the important thing with that is that the development of new technologies is much harder than the improvement of products, but it still depends upon the combination of products from other technologies. So much for the technology landscape, and as I said, Lise will cover a little bit more about how we've implemented that and try to capture that in the model in a second. So this is the agent-based model foundation proper. This is a model of company behavior. And this is the sort of schematic of behaviors, company behaviors we wanted to capture in the model. So companies operate within a subset of technology specialisms. Nigel had that, has that in his model as well, in which they develop their products. Their new product research focus, i.e. what products they're going to work on, is guided by various things. So it's their own technology specialism, their knowledge of how many other companies have products in that technology, and their appetite for research risk. So riskier companies are happier to explore technologies where fewer products have been developed by others, and be more adventurous. Research effort has a cost, which is measured in terms of time. It's higher for products whose prerequisites, parent products, if you like, are not yet available or known to the company doing the research. And knowledge of new prerequisite products that have been developed by other companies isn't immediate. There's a knowledge lag. It takes time to filter through. And finally, research results in a discovery if enough time has been invested and the prerequisite products are available. So these are the elements of kind of company behavior that we try to capture. I've covers the rationale for the work and some of the conceptual thinking that went into it. I'm going to hand over to Lise now, and she'll talk to you a little bit about how it's been implemented and importantly, how we've used it with our work at Catapult.
Thank you, Nigel. So yes, as Nigel has mentioned, we first developed a model that describes how technologies are related to one another and how they give rise to one another, and also how some technologies serve to fulfill radical new needs that maybe 10 years ago we didn't even imagine. So the way we build this technology landscape, we do it in a step-by-step process. So we'll start with very few products at the most basic level. And then at every step, we add a new product and we choose the dependencies for it. So with dependencies, there's kind of two types. One would be things that physically go into the new product, like a chip going into a laptop. Or it could be things that you need to discover something, but then you later on don't need to go into the product or to develop the product, say some very specific lab equipment. So let me explain to you what you see in each of these three boxes. So there's screenshots from an animation, which is on the next slide. At the top, you can see which technologies exist and which needs they satisfy. So all the colored boxes exist, and the one highlighted in red is the one that is being developed at that step in the model. The orange one is the technology. So you can see that at the bottom one is the technology that it stems from. So the bottom plot then tells you how many products exist in each technology at this time in the model. So as I said, there's three ways of adding products to the technology landscape. The first one is adding a product into an existing technology on the left. So you just improve on the current best product in that technology. For example, you add a faster chip to a laptop. And this is what Brian Arthur calls standard engineering. So in this example, technology 3 has one product and we're adding a second product. And the needs at the top just stay the same. The second way you can add a product is by adding a whole new technology, which you derive from another technology in orange at the bottom. And so it serves more or less the same needs. So it could be a laptop instead of a desktop. In this example, you can see that technology 19 serves needs 1 and 2. And we start at the lowest level of product, so level 1. You can see that at the bottom. And so the last way of adding a product to the tech stack is by having something that just has an entire new need, something like blockchain. In this example, you can see that technology number 18 is the first need ever to, the first technology ever to serve need 11. So I promised you an animation and you're getting it right now. It's a bit wonky at times, but you can just see how we iteratively built this technology landscape. This is just the first 100 steps. And in the model, we actually use, I think, 1,000 or even 10,000 steps. So now that we've got a technology landscape, we need to let our agents, which are companies, we need to let them explore it. So at every step or time step, or we also call it tick, in the innovation model, companies first have to choose a number of technologies that they're interested in, and then within those technologies, a product that they're going to try and develop in that time step. So the technologies that they decide on, that's a function of the type of company they are, and I will talk at length about that later. But once they've chosen which product they're going to research, we have a step in which we determine the cost. And so the cost depends fully on the parent products or the dependencies that we defined in the technology landscape. So if the company owns a dependency, it will cost them less to make the product than if they only know about another company having it. And so looking at the next step then, once the company has invested enough into a certain technology and all of the dependencies for the product are available, the company can discover the product. And then we just do some bookkeeping. So we keep track of which company has found what, and we keep track of expenses. And so crucially, and Nigel mentioned it as well, we also build a knowledge lag. So other companies won't know about your company's development for a number of ticks. And this is a free parameter in the model which we can play with and which I will play with later. So in this model, there are many levers. There's many levers to the technology landscape as well. But what I've done is I've picked one technology landscape, so I've generated one. And all the innovation models are run on that same technology landscape. So that's a fixed value. In the innovation model, I've got 100 companies. I start off with company number one owning product number one in technology number one. So very, very meager beginnings. And then I let the simulation run for 200 time steps or ticks. Because there is huge stochastic variation and randomness involved, we use multiple reps. I've used 30 repetitions or Monte Carlo runs. And each of those runs for, say, about 2 minutes, either locally on a laptop, or we've also used our AWS and use our simulation platform for big parameter sweeps. So I'm just going to show you a little bit of the model behavior. And to show you that, I need to tell you what I'm going to show you. So I keep track of a whole host of things in this model, but I'm only going to focus on 2 here. One of them is the number of unique products discovered in a simulation, in one run of the simulation. So you can look at this throughout time, and what you get is a cumulative count of how many unique products have been discovered. Obviously, if we want to compare multiple runs, looking at sets of 30 traces of time series is going to be a hassle. So what I do is I just summarize the end of that run in a box plot, as you can see there. So as I said, one measure I'm looking at is the number of unique product discovered. I also look at the total number of products discovered. So if 2 companies find the same product, it's only counted once for the unique products and it's counted twice for the total products. I've mentioned before that there are different types of companies, and I've actually used 2 types of companies. So type 1 is a more conservative type of company. They focus on research and technologies that they already have experience in, or technologies that other companies have a lot of experience in, so kind of popular technologies. The second type of companies, type 2 companies, are much more innovative. So they will look for innovation in new technologies and unknown needs so far. What I've done here is I've run a set of simulations where I change the mix of the type 1 and type 2 company firms in my agent population. And so if you look on the left, you can see the number of unique products discovered. There is a peak at around 85% there, which is interesting because you might think that the more innovative companies you have, the more unique products you'll have. And so you would peak at 100%, but you don't. And this is something that Brian Arthur also points out. You need some more conservative companies to push forward the existing technologies through standard engineering, because only when those will have been developed, they can be dependencies for products that are innovative in the sense that they might serve a new need. On the right-hand side, you can see the total products discovered, again, as a function of the percentage of innovative firms in the agent population. And you see a totally different story here. So what you see is that there is a peak somewhere around 30–40%. And that is somehow, well, I guess if you look at it from a consumer perspective, there are less products and technologies available, but those that are available, there will be more manufacturers producing them. So consumers will have more choice in that type of world. I could say so much more, but I'm limited in time. So I'm just gonna talk about some of the interventions that we modeled. So we wanted to model the type of interventions that Digital Catapult undertakes. And so there's two examples here. First, there is, we wanna look at the de-risking that Digital Catapult does by reducing some of the cost of research for companies, for example, through letting them use their testing labs that are dotted all around the UK. The second type of intervention is the one about networking. So Digital Catapult tries to introduce companies to each other. So for the first one, as I said, it's about reducing costs. What happens is that at each tick, one innovative company receives a number of ticks or units. As I said, time is, I think Nigel said it actually, time is money. So to get to your cost of development, you need to have enough ticks to invest in a new technology. And so what you can see is that this obviously really boosts discovery, both in unique as well as in total products discovered. The next networking scenario then. So we implemented a scenario in which the Digital Catapult agent sets up connections between companies, typically a company trying to get a first product in a new technology, and a company that has dependencies that the new company doesn't know about yet. And so there's a double effect of setting up this kind of intervention. First of all of the knowledge lags between the two companies that are connected completely disappear. So there is an advantage there, especially when there is a long lag in knowledge. And there's also an impact on the cost aspect. So products owned by a connected company, you can count them as owned rather than a more expensive known product when you're looking at the cost of a new product. So the effect of the number of connections made at each tick, which is what I plot here on the x-axis, is actually very noisy if you look at unique products discovered. I would say there is a small positive effect, but that's about all you can say. What you can say is that in the total products discovered, there's a clear trend upwards. So it makes sense to invest in these type of networks. So that was a really, really quick tour of that model. We've got a bunch of next steps listed. I think, first of all, there's a lot of exploration work done on what we already have. We've done some of that. I did not have time to show it. But I think more excitingly, what has to go on top of it is a sort of economic model in which consumer demand and consumer needs drive the uptake of certain new technologies, and you can model things like being locked in by contracts, etc. And that will then drive firm birth and death processes. And so lastly, and definitely the most challengingly of all, is we have looked at ways in which we can use existing data to calibrate this model. So that would be the next phase. Thank you very much.
Thank you very much, Lise. Again, we're very excited about this project, and obviously if everybody has any questions, obviously we've got time for some discussion afterwards, but please feel free to contact me or here at the Digital Catapult, and we'll be able to talk through with you more, and this is an early stage. So I'm conscious of time, and I want to hand over now to Sergei Martorell. Sergei is co-founder and CEO of Glass AI, and we've worked extensively with them, so very, very pleased that Sergei is joining us today. So fire away.
Thank you, Brian. I hope you can see my screen. No, not yet. Right, I hope you can see my screen. Yeah, great. Thanks, Brian, and Digital Catapult for inviting me to this seminar. I'll try to be quick as I'm conscious of the time, and thanks everyone for listening in. The purpose of my presentation is to talk about how the web data can potentially be integrated with some of these agent-based models. My name is Sergio Martorell. I'm one of the co-founders and I'm the CEO of Glass AI. We're a UK technology company that has developed an AI system that reads the web at scale and can understand its contents. And the technology so far is used by government, academia, nonprofits, and increasingly corporates for different use cases. So what I'm going to do is I'm going to talk about some high-level macro trends. In fact, Andy Haldane has touched upon some of them. And then I would use Glass AI as an example of how the web data can potentially be integrated into some of these models. So the first trend I wanna mention is, as I'm sure you know, over the past few years, there's been an explosion of content. 90% of the world's data was created in the last 2 to 3 years alone, according to IBM. The data, a lot of this data is unstructured, and it comes in various forms. For example, it comes as audio, video, and also textual data, which is our focus at Glass AI. And the data can also be found in different platforms. One of these platforms is the open web. And in fact, the open web has become too big to read. This is a trend that is set to continue. The explosion of data is set to continue, and ABMs thrive on data. But what do I mean by the open web? By the open web at Glass AI, we define the open web as 5 to 7 buckets of open data that can be read by machines, and can be understood and structured, and can potentially be fed into ABMs looking into the economy or public policy. Probably the main one is the websites of organizations. We've estimated there are about 35 million organizations globally that have a website with content. Half of those have English content. Then, as we know, news, blogs are also a key source of data and insights about the functioning of the economy, signals about companies and consumers. And then, obviously, social media. Social media is the other main bucket of open web data that, at least at Glass AI, we're reading. We're reading these different sources of information. And then we have others. Increasingly, governments are publishing information about sectors, businesses, and then we have other buckets of data like academic papers, jobs, patents, and so on and so forth. So this is what we mean by the open web when we say that we can read and understand some of this content. The second trend I want to highlight is the fact that there has been an acceleration of the adoption of digital channels by consumers and businesses. Now, the trend was already there. And if we're looking, for example, at internet sales as a proportion of retail, you can see that the trend was already there. But COVID has accelerated this adoption. What this means, and why I think this is important, is because the digital economy is increasingly becoming a copy of the real economy. And this has been acknowledged by, acknowledged by several institutions, for example, national statistics offices, that are paying more attention to some of these real-time indicators that can be inferred from reading the web on a regular basis. For example, job ads, pricing data, other web data, and we've been contributing to some of the efforts at the ONS. This is a trend that we believe will continue. So we have an explosion of data, and increasingly the digital economy is becoming a copy of the real economy. The third trend that we think is key, and this is something that Brian mentioned when we had the discussions prior to this webinar, was the emergence of new algorithms, new data collection techniques that allow us to collect this data, to understand this data, to structure this data. And in fact, this is what we do at Glass AI. That's where we come in. The technology we've built over the years is a system that reads the web and can structure and understand the content. It's technology we've developed over the years with links to UCL, and we got seed funding from Imperial College London. We came out of R&D at the beginning of 2019, and the focus of what we do is in machine language understanding, which aims to give computers the ability to understand not just keywords, but entire sentences and eventually entire paragraphs. To put it simply, we've developed an intelligent crawler that reads the web. For example, it will read a domain and understand that a domain belongs to an organization. It will read content like the description of the organization, the topics that define that organization, the people, the biographies, the products and services. We've done that for example, for the Northern Ireland executive as part of the Brexit negotiations. And it allows researchers, analysts, data scientists to answer more complex questions. And it will have the potential to be applied to ABM models. Since we came out of R&D, we've worked with corporations that use the capability to find hard to find clients, but also government organizations, think tanks, universities that are applying this capability around different use cases. One example is to better understand emerging sectors. For example, we've collaborated with Digital Catapult and helped them map the virtual reality sector in the UK. These are sectors that are very hard to understand and are very hard to map using official sources. This has been done across many emerging technologies, and not just mapping the technologies, but also mapping the applications. So for example, which companies in the UK, and we're currently doing this for a big professional services firm, are adopting certain technologies, are adopting virtual reality, are adopting AI. We read the news, press releases, job ads, and that gives us signals, that gives us evidence that allows us to map these, how these technologies are being applied, how these technologies are diffusing within the economy. So that's just one example. Another one involves more societal issues, so less economic, more societal issues. For example, the gender representation within companies in the UK. Obviously, this can be done via surveys, but this can also be done from reading the open web and understanding what's that gender representation, or actually non-representation. For Brexit, understanding the products and services that Northern Ireland sells to Europe, or sells to Great Britain. And there have been many other applications. So this is just to illustrate some of the potential of these new data collection techniques that could potentially contribute to ABM models. And the last slide I want to show before my conclusion is another application, is the capability to monitor companies and potentially people around any dimension. One of these projects that we're currently doing, we're helping academics and think tanks better understand how UK businesses are responding to COVID, the challenges of COVID. So we read several thousand websites of businesses, we read thousands of news sources, investor relations sites, and others, and that provides changes in the data, how those businesses are reacting, how things are changing in terms of new openings or closing down businesses. It gives the trend, it uncovers relationships and other areas. So I wanted to run through the presentation very quickly. My conclusion is, and it's been discussed previously, that how ABM bottom-up perspectives could augment the top-down approaches that are widely used already by policymakers and economists. ABM models thrive on data, and what we've seen is that there's an explosion of data. If we focus on the web is increasingly a copy of the real economy. But today we have the techniques, we have better data collection techniques to understand, integrate the richness of the web's data into agent-based models. So that's my presentation. I hope it was useful. Thank you.
So guys, yes, that was great. Thank you very much. And we, again, value the role and contribution that Glass AI have had in helping us sort of identify and explore these emerging technologies that we're working with and the locations with it. If I could invite all panelists just to come back on screen and unmute microphones. So we're just waiting for Nigel and Alan. There we go. We have had a number of questions come up on the Q&A, and so I'm going to use the next 20 minutes or so just to try to do these. I'm going to take the first one here, and I'll invite you all to answer this in no particular order. So we have a question that says, the models that we've been talking about are very complex assumptions. So we have a challenge. So how can we effectively communicate these to policymakers so that they understand their features and their limitations? And if I could take the thing of going to Alan first, if you have a view on that.
Yeah, it's an interesting question because, in fact, it sounds as if the old models, the standard economic models, were easy for them to understand and easy for them, but a lot of very sophisticated hypotheses were hidden in those models. So what happens with agent-based models now is that you actually specify carefully what each agent does, how he reacts to others, and so forth. And so that's actually upfront. But I think the idea that these are more difficult to understand is actually the wrong way around to look at it, because, you know, with these agents who interact with each other, and they have simple rules for doing that, usually sort of heuristics for doing that, as opposed to the other models which have a lot of mathematical assumptions in them, which are buried. You don't see them. So you think that these are simple relations, but in fact, they're not. They depend crucially on the mathematical assumptions which are never seen. And the difference with agent-based models is that you could actually explain to people clearly what guys are doing in it, what firms are doing in it. So I think that's a big difference. And once people get then a head around that, they actually find them easier to understand than what's going on in more sophisticated economic models. So I would say that if you allow people to play with these things a little bit, you very quickly get them into understanding what's going on. But many people don't want to play with them. Just want to sit there and accept what was given to them without worrying about what's going on in the model. So that's a start to the answer, but I'm sure other people have things to say about that.
Yeah, I mean, I very much agree. I mean, you know, as an economist, when you're actually talking to people about something around, say, competition policy and so forth, and you're looking at the relationship between concentration and competition, when many of the assumptions underpinning those models are very abstract, and the policy is overly simplistic because of that abstraction. And I think what the value of ABMs is that they do look complex, but you are building around normal behavioral assumptions that people are there, and the emerging properties are very informative. Others, Nigel Guy or Nigel and Lee, Sergey, have you a view on those, given your extensive experience?
Well, I'd just like to say, to continue Alan's theme, unlike traditional models, the way to build these kinds of models is with the people who are interested in the results. So it shouldn't be just a matter of you develop a model in your office and then you kind of throw it over the fence and say, here it is. Not at all. It ought to be a collaboration. And the point of that collaboration is partly that the people that you're collaborating with have a real understanding of not only what the model does do, but even more importantly, what it doesn't do. So in my experience, that's the only way to build agent-based models that actually have any influence rather than just being pretty.
I totally agree with that. Well, totally agree with both of those main points. I think, you know, the idea that agent-based models are somehow more complex or embed more complex assumptions than a lot of the models that got used in kind of finance and economics is, I don't think, true. And as I said, in principle, because they are behavioral and transparent in most cases, you can get a feel for what's going on in an agent-based model in a way that you can't with a model that's kind of built in some kind of complex spreadsheet or financial software that hides its assumptions. And yes, Nigel's point about collaboration also very important. I mean, most of the models that we've developed over the 8 years we've been doing this, the best ones have always been done with kind of close relationships with the people we're developing them with. What you need to do that is to have some kind of a framework, a language, a way of talking about what you're doing that makes it clear in the early stages of the process what the model is going to contain and how it's going to work. In the presentation we did, we just gave us some of the tools that we've used there, like the boxology. That really helps. But the other thing, just to add to that, is I think the more you can get people to use these models and interact with them themselves, then the more they'll feel comfortable with them. And it's not always easy. It's not always easy to expose a model in a way that a policymaker or people like that can actually use, but it's worth the effort, because if people are able to play with it, move the levers around, understand how it works, then it becomes more familiar and less scary, if you like. So I think that's another thing that I'd add.
Okay. So, Guy, anything to?
No, nothing to add, right?
Great. We have another question that's actually focused around some of the presentations on innovation. So, so we actually sort of had 3 models of innovation. So the question is, what do you think gives people confidence in one model rather than another? So how do we give people that are new to agent-based modeling confidence that their investment in it will provide useful insights if you can build such different models around the same context? So really the battle of ideas. I mean, we've talked about different ideas and theories, and we've modeled those. How do we build confidence in the adoption of these models if there are different methods of dealing with the same problem? And I'll open it up to.
If I could jump in here, actually, my feeling, having heard the sand table model, is that it isn't that different. Many of the kind of basic principles are the same as in the skin model, and that's great. Obviously it looked a little bit different because the user interface was different, and some of the ideas were different, but not a lot of them. It seems to me that the conclusion you should draw is exactly the opposite. Here we have 2 essentially completely independent attempts to model innovation, which end up with frameworks which, in many ways are rather similar, and that's good news.
I think
I was thinking the same thing. I was thinking, well, are they really that different? I mean, I think your model, Nigel, goes a bit further in the direction that we sort of outlined as some, where we wanted to go next in terms of putting in birth and death, notion of sort of economic success. But apart from that, I mean, there's also the piece about the building the technology landscape and the behaviours in terms of things that you're capturing, what we're trying to capture, and certainly presumably some of the results are going to be very similar. So I wouldn't, I mean, see your work made me think we should talk about this. Let's exchange ideas. It's not like it's it's coming from a completely different paradigm at all. So
yeah,
I think it's more in common than people.
The test of most sort of standard economic models is how well they forecast, but that's not a very good way, I think, to think about how to value models and so forth, and of course that's one of the explanations for the fact that people have very little confidence in economic models, because they're usually lousy at forecasting. So I think that's not the right criterion. People should have more confidence in them if they feel that the general pattern of what's happening in these models corresponds to what they observe in the world that they work in. And the more that happens, then they start to see features emerging which are features which they actually observe. And I think that reinforces things very much more than hoping that these things are going to project something which is then realized and you say, oh, wow, that was a good forecast. So I think it's the criteria that we use for judging what's good rather than the sort of standard argument, which is, let me just look at how well that forecast next year's GNP or whatever, you know.
And in fact, you know, building models of innovation is a classic case where it is, as it were, almost by definition, you can't do prediction. I mean, if we could predict innovations, they're not innovations, in my view. So a great. Well, so what if you don't predict, you don't forecast? What on earth is the use of these models? And my answer to that is that these models give you the opportunity to get a much better understanding of the complex processes that are involved.
Yeah, we would echo that. So one of the challenges is that, you know, a policy intervention is clearly to change a direction. So it's to change a situation that occurs now. And in our case, because we're working with very advanced disruptive technologies, the likelihood is that, you know, the new future is going to be very different. And so, you know, it's about exploration, about enabling us to explore what these potential futures might be. But I think one of the challenges is actually, you know, the policymakers who make the decisions or invest the resources need to be comfortable that this is the best approach. And I think, again, as we've been finding with Follow the Science, there is no defined science box with a book that you can just refer to, and we need to have this dialogue as a process. I think that's very, very true there. I have a quick question for Sergei, actually. You talked about the web and one of the benefits of that being that websites being written in English. So the question sort of come back saying, is there a concern that this may in part create some sort of reinforced bias from the data? So do you have a thought on that?
What I meant, and apologies if it wasn't clear, is that our estimate of 35 million organizations with a website globally, half of those have the content in English. And just to get a sense of the size, currently our system has been tuned for the English language. So we've been focusing on the UK, the US, Canada, and we're developing the algorithm, sort of the language model, so that we can read the websites and the news from other countries. So that's what I meant by the content being in English. It's not that the content is only in English. Only half of the content of company websites is in English, as per our estimate.
That's great, thank you. We have another question which I'll put to all of you. I think it's quite a broad range question. So why do you think that ABMs are so much more difficult to be accepted in academia than other radical changes such as behavioral and experimental economics? So, you know, it's a strange question to ask the panel here, who clearly very experienced and have a lot of research and output in this sort of area. But for myself personally, I found it a big challenge over the course of the last sort of 15 years or so working with it, but getting it sort of accepted. Clearly, for me, there's an echo chamber, and I'll read the right papers and I'll follow things through. But for yourselves, ABM doesn't seem to have been accepted as quickly as, say, other developments and other ideas within broader economic theory. Do you have a thought on that?
Yeah, I have a clear thought on that. I started life as a general equilibrium economist, a mathematical economist of the worst sort. And I have seen the profession evolve. And I think I've rarely seen a profession which is so slow to take on ideas from the outside. I mean, other fields like physics, like biology, have moved radically. You know, biology moved over to molecular biology, over to systems biology now, in rather a short period of time. But that hasn't happened in economics. And you might ask yourself why. And I've never found the answer to that. The profession is very much focused on what has been done in the past. And it was Mankiw, the who was head of the, and certainly not a very experimental economy, a very, what's the word, progressive economist. What he said was, you know, the reason that that most research in economics hasn't had any impact on the macroeconomic policy is basically because it's advanced the science, but not the engineering. And what we need is the engineering to actually do things. And so policymakers have basically not taken on board all these sophisticated advances. And Paul Romer, who was the chief economist at the World Bank, said essentially the same sort of thing, that there's been a huge split between the theory, which has been developed in a more and more sophisticated way, and the practice that is actually looking at what we should do. And I think although people say we use DSGE models, famous models, to inform policymakers, in fact, policymakers don't look at DSGE makers. They try and get some vague lessons from them. But with agent-based models, what you see is that you actually can understand the nitty-gritty, how this is working. Somebody explains it to you, and then you can think about doing that. But there's a reticence, and it's a very simple answer, that people think that their human capital is being threatened. And economists who've been brought up to be told that they're doing the smartest possible things, and that everybody in the world is optimizing and that'll all work out, are sort of reluctant to accept the idea that in fact, with different techniques, in some sense simpler techniques, we could actually do better at explaining the world, not necessarily forecasting the world, but explaining the world. And last remark, Hayek, who's an economist for whom I have no love, but he said, you know, there are no laws in economics. They are just patterns, and we have to learn to recognize the patterns. And everybody said that's nonsense. But I think there's some serious truth in that. And in some sense, that's what agent-based models help you to do, to recognize the patterns that are out there, rather than say, I'm going to tell you exactly what's going to happen.
I'm glad you said that, because one of the reasons I got into agent-based modeling about 25 years or so ago was to model market processes a la Hayek. It's good to see that sort of echoed. Nigel and Nigel and Lise and Sergey, have you any thoughts on that?
I think the observation I'd make briefly on that is that, and I think Alan's getting at that, there are a lot of embedded practices. You know, I can't speak for the economics profession, I'm not an economist, but there are a lot of embedded practices everywhere, and ways of doing things. And there's a resistance to, it's an institutional resistance, it's practice level resistance to looking at new things and sort of saying, well, you know, we said this before, and actually we're wrong. We start to see that it requires leadership. People like Andy and others are obviously providing that leadership to change the way that those practices operate. But to me, it's about embedded practice. It's not about the science. And I think we're starting to see more and more work going on. It'd be nice to see more investment from kind of commercial and government organisations into ABM. But I think Dorian Farmer says, you know, has a slide somewhere where he just talks about the level of investment in DSG versus ABM. We've still got a long way to go before we get to that level. But you know, I think the real resistance is about practice.
Yeah, I mean, one of my sort of endearing memories, as I say, of moving into this, or it was actually sort of modeling complex systems as opposed to sort of ABMs. But it was actually, you know, Nigel, you've heard me mention this before, but you know, there used to be a BBC program called The Net, and on that program once was Paul Ormerod, and it was, you know, his book Death of Economics, and you know, why don't economists play SimCity? And this was back in '96. So obviously, again, it was about, you know, using those sorts of models and rather than relying on traditional forecasts. And so 25 years forward, and we appear to be asking those same questions, which I don't think is a failing. I think what we've seen today is that the availability of the data, the computational power that we have, the growing acceptance that we do operate in an environment of uncertainty and of risk, and that things do emerge very quickly, and new technologies all make ABMs the appropriate method for exploring those and doing so. I'm conscious that we're sort of only about a minute or so left. Open to everybody of any last reflections on the topic of today.
Can I say very quickly, I think one thing that I've noticed is that there's a huge reaction amongst young people. There are all sorts of young people organizing things, rethinking economics and all other sorts of names in various countries. And all of them are hungry for something different than what they're taught in standard economics courses. And so maybe we will start to form a new generation of people who are much more open to these things. And the one danger for ABM, like other things like networks, is that economists will say, very interesting stuff, really great, but that's on the side. You know, the mainstream will keep going and we have these very interesting developments, but they're on the side. And I think that the young people hope that these things will be moved into the center. That's my real hope.
Yeah, any innovation takes at least 15 years from the lab to actual use. It may be getting quicker, but I don't think we should be too pessimistic. The situation for agent-based modeling as compared with when I started is now utterly different. And I expect in 5 years' time, it'll be utterly different and better again.
And I've had sight of some of the obviously presentations for the next couple of panels, one of which addresses this very good point. So I would encourage people. My thanks to all the attendees, but we have a number of panels running on. The next one I think is at 12:30, and those links are available to people who registered for the event. Just my final point to say thank you very much to all of the panelists. This has been a long process in coming together, and the environment has been quite challenging, but I thank you very much for your patience, for your contributions to this. These will be put onto our YouTube channel, so we'll all be able to look back in posterity. Yeah, I thank everybody, and have a good day. And I hope to see many of you at the next panel, which is looking at physical infrastructure. So everybody, thank you very much, and
thank you.
again soon.
Thank you.
Thank you.